conceptuality video 5 that goes with the writing, or pure conceptuality. In the writing, we talked about frequency and how frequency is frequency squared equals the number of triangles in the plane, right, or in the area. So that this is a frequency 4 triangle. If it's got 1, 2, 3, 4 units of length, and there are 16 triangles contained. So 4 to the second power is 16. You know, it's the similar mathematically the same as figuring the area of a square, but I don't like to think about squares. Here's a 2 frequency triangle, right? It has integrity. It is. I mean, this thing has integrity. It displays its triangleness perfectly well. But each triangle is flat, but the whole thing is hinged, right? So there's no flatness. Even though it's all triangular, each triangle represents the flatness. Otherwise, the flatness does not exist. Okay. And just for dramatic example, here's the square thing, right? It has no integrity in any way, right? I mean, it's squares are not complete. They're incomplete. They need to have they need to be stabilized and turned into triangles. Okay. I want you to understand also that all this stuff, this is just fishing line inside tubes, right? I mean, there's no glue or anything in any of this, right? I mean, that's important. I mean, to realize these are self-structured. They're held together by push-pull forces, right? There's no, no gluing or anything like that. Okay. Now, I just want to review the tetrahedron a little bit. Here it is. It's absolutely complete. There's nothing unresolved about this. There are no vertices. There's no place to put anything. No unresolved vertices. Right? It's complete. It's whole. It's a unitary oneness that's finished. Okay. Now, for a dramatic effect, I'm going to pull the octahedron out of the 2 frequency tetrahedron again, as I did in the other video. I just think it's important to see that this idea of the integrity being the triangulation, and that the octahedron is actually what is now stabilizing the 2 frequency tetrahedron. All right. So out comes the octahedron, and it has its own integrity, right? Because it's a 1 frequency. So out of the 2 frequency tetrahedron comes the 1 frequency octahedron. Okay. So this is the AB 1 frequency octahedron. Right. Now, it isn't as resolved as the tetrahedron. There is the possibility of connecting new points in space, new locations in space that have been created in these vertices of the octahedron. We can go through here, we can go through here, we can go through here. So there's 3 possible connection locations. Right? Now here it is already done. Right? So we have a new dimension, because this AB length here is not sufficient to go through to connect these vertices. Can you see that? It's too short, right? So we've established for the first time in all of this construction, this self-manifesting geometry, we have a new dimension. And what is that dimension? Well, here's a way of seeing it. There are 2 things I'm going to show you here. Number 1, by connecting these vertices, we have divided the octahedron into 4 parts. And I'll probably have a model that will show you this a little bit better. But there's 4 sections here that are represented by this piece of paper that I put in here. Okay, that divides it perfectly into 4 pieces. All right. Now, what is this piece? What does this look like? Well, this is just simply a square, right? And we know that this dimension is 1, right? And what is this? This dimension across here is gives us a perfect equilateral right triangle, right? So if this is 1 and this is 1, uh, 1 squared plus 1 squared is 2, and so this length here by the Pythagorean theorem has to be the square root of 2, right? So the new dimension that was self-created is this beautiful thing with the simple identity of the square root of 2. So there's a whole rationality to this. There's a wholeness in the rationality. Everything that comes out to everything makes sense. There's no unevenness in it. It's all rational. So here we have the octahedron. We have now determined that the dimension of the interior dimension of the octahedron, if the edge length is 1, this new length, which is now the height of the octahedron, is the square root of 2, right? That's pretty handy. Now, that is also at the same time we connected those vertices of the octahedron. We created the XYZ coordinate system, XYZ, right? And the XYZ coordinate system in the context of this octahedron has the square root of 2 as the length, or 1/2 the square root of 2, just going to the center, right? So that these are discrete lengths. There's no, you might say, well, the square root of 2 is irrational, but it's not. Look at it. It's determined exactly by the octahedron. So the square root of 2 is, all you have to do is measure it. There it is. That's the square root of 2. No decimal points going off into infinity, right? That's the system of measurement that's the language of mathematics that makes it go on forever not to resolve. But we can see that it is automatically resolved by nature. The square root of 2 is a real number. Okay? It's a real length. Let's put it that way. Okay, I think that's probably enough for now.